Hello, everyone. Welcome to Foresight Space Group. Today we have Chiara Marletto here with us. She'll be giving a brief overview of her work, and then we'll pass it off to Creon to conduct an interview. So thank you so much, Chiara, for joining us.
Yeah, thanks a lot, Lydia, for organizing this and for inviting me. So I will just really very briefly introduce myself and my work. So I am a research fellow in Oxford at Physics and Wolfson College. And I've been working in, broadly speaking, the area of quantum information theory. So this is my background. But about 10 years ago, I stumbled upon a very interesting development in the area, which was called constructive theory. And this was proposed by the quantum computing pioneer David Deutsch, who just gave a talk actually during my PhD here, and I was very inspired by it. And this idea of constructive theory is to go beyond quantum computing itself to cover areas of both physics and computation that are not included in the theory of the universal quantum computer. So it's really about investigating, on the one hand, constructors, which are these more general machines that are programmable to compute, to perform anything, not just computations like computers, but actually to construct anything that's physically possible. And then on the other hand, is also a tool to come up with new physical principles. So it's like a new theory of physics. And I think at the time, David kind of laid out the foundations of this theory in a sort of philosophical way. And then I ended up actually not just doing my PhD on that, but also I found it so promising that I decided to apply to a number of problems in physics. And lately, I think what happened was that some of this work led to a very interesting development on the experimental side. So I'm currently kind of pushing an effort to realize a very interesting experiment to test some physics that really goes beyond the two theories we currently have, with general relativity on the one hand and quantum theory. So this experiment is to test quantum effects in gravity. And so this kind of my kind of brief overview of my research, and I'm very happy to engage in a nice discussion or interview with you. Thanks.
Okay, so I'm going to start and ask, there are some other similarly named research programs. Or similar flavor. There's Wolfram's program, which has to do also with what rules are possible. And then there's also the Lee Cronin's assembly theory, and that's mostly about molecules, but it's got a similar name. Do you want to first discuss the Wolfram program and the Cronin program and how yours differs?
Yeah, I think they're very different in a sense that, so Wolfram is really rooted within computer science, and it takes things like computation information, like primitive entities. So he doesn't really worry about how they are connected to physics. Whereas constructive theory is more like a theory of physics, is really trying to unpack the principles that allow for phenomena like information and computation, thermodynamics and other things to be possible within our own universe, not just in a computational world, not in the solar automaton world. So in that sense, it's also different from the original idea that von Neumann had about constructors. The name of constructor theory comes from that. Von Neumann was really interested in the computational aspect of constructors, but didn't investigate what it means to actually have a physically possible constructor or universal constructor. And so in that sense, our take is much more into fundamental physics rather than in computation. And for Cronin, I think that's in a different direction, in a sense that the assembly theory program is more like a way to look into quantifying complexity ultimately in the biosphere, or let's say in our universe. And somehow, again, is very niche. It sort of applies in a sort of context of biology and chemistry, whereas we are trying to provide a really fundamental framework for physics, out of which you can then find principles that tell you what are the limitations of actual machines. But I think the focus is on the ultimate principles of physics.
Understood.
So that's kind of the difference.
Great answers. Now, I apologize that these are not, I should have ordered these and clustered them, and I kind of didn't, but so they may jump around a little bit. And
that's
so
great. I like
feel
that.
free to jump around yourself. So next one, in your write-ups, you say this can, quote, test quantum effects of gravity for the first time in history. How so? And I mean, there have been others proposed experiments, for instance, vacuum birefringence, vacuum dispersion, Lorentz non-invariance. There are proposed experiments to look for effects beyond GR or at the frontier of quantum theory and GR, various black hole things too. So will you say, what is it that yours does quote, for the first time in history, experimentally.
Yeah, so this is a theoretical idea at present. So when we're talking about this, is like if it were to be realized, that's always the proviso, and that's part of what I'm doing at the moment. So I'm trying to sort of realize the experiment. But from the theoretical point of view, the fact that makes this a game changer, this proposal, is that it's possible to realize it at low energy. So previously, it was thought that most experiments to test quantum gravity would have to harness very extreme regimes where with very high energy, black hole physics, regimes that are not easily accessible in a laboratory. So which means that you would have to, either they are near impossible. So some people actually thought that because of this reason, we may just give up on quantizing gravity simply because these quantum effects are so hard to test that it doesn't make any difference in real life whether they are there or not. And so lots of skeptics of the quantum gravity program just wanted to give up on the fact that gravity is quantum simply because it looked like it was very difficult to test these effects in a laboratory. Whereas what we proposed came from a different angle, and this was some work I developed with Latko Vedrol here in physics, and there's another team in London also led by Sugato Bose who actually came up with a similar experiment with a different rationale. So kind of we converged on the same setup. We've thought of something from the angle of information theory, which is why this is so exciting, because this shows you that if you look at some problem from it with a different lens, you suddenly see it, in a sort of fresh way. And it turns out that if you look at masses that interact with gravity and can be also treated like qubits, so they are low energy masses, they're not moving very fast, they're going slow in a sense compared to particles in an accelerator. And you can manipulate them quantum mechanically the way that you would do in a quantum computer, for example. Then the order of magnitude of energies and masses that you need in order to witness these quantum effects is much lower than expected and much closer to the masses that can currently be manipulated in these experiments. So that's the key difference. And that's the key tool that's used by the experiment is entanglement, which is a chiefly quantum information, quantum phenomenon, and it's kind of the thing that powers the quantum computer. But it's used in this exotic regime where we are using gravity to perform a sort of quantum computation, if you like.
Okay, so maybe you could go and describe the experiment or thought experiment, I'm not sure which it is, and then in particularly because of the nature of this group, can you say whether this experiment needs to be done in space or can it be done on Earth? But I guess we should first get into the basic description of the experiment.
Yeah, so the basic description is very much abstract in the sense that you don't need to think of a specific technology. You have two masses, which are about a nanogram, so like the size of a cell, of a human cell, is that kind of size. And they are placed in a quantum superposition of different locations. So it's a quantum state of each mass being here and there. So you have two interferometers that are next to each other. And at this point, you need to isolate the masses in a way that other forces that are competing with gravity are sufficiently low or distinguishable from the gravitational interaction, which is the difficult part, experimentally speaking, and let the two masses interact gravitationally. And this interaction leads to some entanglement between the two masses. And entanglement is simply a kind of correlation that you develop in quantum systems. And it can be tested very well. Its techniques to check entanglement on quantum systems are already well developed. And so you wait for this entanglement, for this kind of correlation to build up between these two objects, and then you measure it at the end. And if you do measure a non-vanishing amount of entanglement, this argument that we have within constructor theory, that's the theoretical part, the legwork, it's done by the principles of constructor theory in this context. This very general argument allows you to say that if you see this entanglement, then the thing that mediated it, the thing that mediated the interaction between these two masses, must have some quantum features. And in this case, if you can say that the only thing that mediated the entanglement is gravity through experimental considerations, then you have a witness of the fact that gravity is quantum, which somehow violates the current description of gravity that we think is the best, which is the kind of relativity, so Einstein's general relativity.
Right, understood. So is this a thing that requires some kind of laboratory far from the Earth and in flat space-time on a geodesic, or is that irrelevant?
Yes. So there are different proposals, different ways of implementing this idea. Some of them can be performed. Some of the proposals are performable on Earth, so in a laboratory space. So in that case, you have to set up the interferometers in a way that the gravitational field of the Earth is not relevant. And so there is some set of studies of how you can implement it this way. You could do it in free fall, and then connected to this, you can do it in space as well. So I think these are all different platforms over which you can implement this kind of idea. And at the moment, people, including the group that I'm collaborating with in Torino, in Turin, are looking into what is the best kind of implementation. And we're betting on a certain setup which can be realized on Earth. But I think once you have that setup, you can also transport it in space and ameliorate it, because in space you have the advantage of certain, noises being reduced and so on. So I think.
And how do you, it seems to me, as with many of these gravity type of experiments, you have to be super careful about electrical charge and other disruptive factors. Have you guys done error analysis on that?
Yeah, so I think what we've been doing so far, given that the equipment is currently being constructed and we are kind of fundraising for that, we've been doing a lot of feasibility studies. And I think one of the main competing forces is exactly electromagnetic forces. And you can, consider neutral objects, neutral masses, but then you have these van der Waals forces that become relevant. And there is a sweet spot of the distance between these two interferometers, which is about 100 nanometers to 100 nanometers between these two interferometers, where the Casimir forces the van der Waals forces are low enough to allow for the effect to develop. So there is always like a parameter space, and we have a nice map of which parameters are suitable. And I think this seems encouraging because it's very close to what people can do at the moment in the lab with some of these molecules.
Excellent. So is there some sort of binary outcome that you're looking for from the experiment? And if you get it or don't get it, is there a possibility of any new practical technology coming about because from this, or is it just a search for knowledge?
Yeah, so it is a binary outcome. So either suppose you do the experiments properly, and then you either see entanglement or you don't see entanglement. And either way, it's like a surprising thing. So if you see entanglement, which is what I think you will see if you do it properly, that will be really like a huge step forward, because it will tell us that relativity as a classical theory is violated. So it has to be modified in one of the ways that is suggested in these quantum gravity programs. But if you don't see the entanglement, then that also means that that's somewhat even more surprising, at least from my point of view, because it means that then quantum theory, the way that's currently merged with gravity at the low energy, is wrong, so that some of the basic principles of quantum theory have to be modified. So one way or another, as I said, I bet on the first, seeing entanglement, but even if you were not to see it, you would be very surprised. So that's really cool, fundamental reason for finding this experiment really exciting. But then from the technological point of view, this would be also a kind of first thing, because it would be a first interferometer where you are harnessing gravity in a quantum computation. So you could, the first quantum computation was ever performed was one of these, you can think of quantum interferometry of photons or of electrons as an example of a quantum computation. It's very simple, but I think that's the basic thing, because once you do that with a single system, then you can kind of build up too many systems. And so far, gravity has been considered like a sort of noise in this context. But here we're using gravity to construct a very carefully designed phase, which is then is the thing that creates the entanglement, right? So it's a gravitationally mediated quantum computation. So in that sense, it paves the way. It's like a first milestone in the direction of a new type of quantum computation, which actually goes beyond both quantum theory and relativity. That's a sort of next, version to like a next version of quantum computing as we know it, which is why I find it exciting. And it sort of bodes well with this program of constructor theory to generalize the quantum theory computation to cover these more exotic phenomena so far haven't been included.
Okay, great. I get it. That actually answers the second question, so I don't have to ask it. The next question, so I don't have to ask it. So skipping ahead, you in your write-ups, I saw a statement you made. You said you emphasize the principle of locality in your discussion and introductions to constructor theory, and you said, despite prevalent misconceptions, these quantum correlations perfectly satisfy the principle of locality. Now, that is kind of a bit of an outlier opinion, right? Because most of the quantum theorists, and from EPR to EPR-Bohm through Bell's theorem, standard interpretations of multiparticle wave functions, they all violate the principle of locality. But you seem to think locality can be salvaged. Can you say how and why?
Yeah, so there is sometimes a confusion of terminology. So locality, in the way that I intended it in that statement, is this idea of no signaling, no instantaneous action at a distance, which means that if you do something over here and you have a quantum system that's entangled to the system I have here and it's far away, there has to be a signal that goes from my region to that other region for someone to find out that I've done something here. So it cannot change in an observable way the state at the other end instantaneously. So, and this fact is a pillar of quantum theory, of relativity, and of quantum field theory. And I think physicists agree on this. However, what we are confused about is the terminology that we use when we talk about this stuff. And so what's been circulating is this idea of Bell non-locality, which is usually associated with these Bell tests for entangled particles that are violated by, so there are some inequalities, and then you have a statistics that's generated by two entangled pairs. You can, by an entangled pair of systems, you can say that it will violate some of these Bell inequalities, and that's a signature of quantumness. The implication of this violation is that you cannot have local hidden variable models for these systems. What does it mean? It means that you cannot have a description that's local and has all observable properties that are definite for the two subsystems. So there's a very subtle meaning, and performing a Bell test and violating the inequality says that whatever system you have at hand cannot be described by these local hidden variable models. Hence the term non-locality for quantum systems, because they violate Bell inequalities. However, that doesn't mean that they violate no signaling. It's still true that even if they are Bell non-local, they satisfy locality. And it's a good thing, because it just means that we can't have this instantaneous action at a distance, which is what confused Einstein initially when he was looking at, this was a huge debate at the time. It looked like they did, but actually after a lot of thinking, people realized it's not true. And this actually, I would say it's, we owe this understanding to the people who studied quantum information, because they managed to really distinguish these two facts. And so locality is the thing we need for the theoretical argument at the base, at the foundation of this experiment. And I think it's, most physicists agree on the fact that this is the case, that both.
Yeah, okay, I'm with you. I mean, local hidden variables are out. You can have non-locality, but also have no signaling. So you're kind of there more in the mainstream than I had thought. So I understand your statements about locality being perfectly preservable, are not a local hidden variables model, but are just a no signaling
requirement. Yeah.
No signaling requirement. Okay, fine. Now, you say that constructor theory addresses quantum entanglement. This seems like it might be critical to the discussion. Can you say a little bit more about that? What does constructor theory, how does it address entanglement, and what does it say to help us understand that phenomenon?
Yeah, I think the way constructor theory is useful is that it allows us to understand some of these quantum information phenomena outside of the paradigm of quantum theory. If you open a quantum information theory book at the moment, you just open it and then you have a look, you will see that all the theorems that are proven inside the book are based on classical information theory on the one hand, but also the formalism and the equations of quantum theory. So the Schrödinger equation is assumed and used throughout when you prove the results that we are using to even build quantum computers at present. Now, this is a nice thing, but what it's not so nice about this is that quantum theory presumably will have to change in the future. We may have a future theory that doesn't use the formalism of quantum theory the same way that classical mechanics was replaced by the relativity and quantum theory themselves. So when you look at these results and you think of things like entanglement, superposition, and various other properties of quantum systems, you would like them to be expressible in a framework where you're not relying on quantum theory's formalism and mathematical features. And constructive theory provides you with that. And it's kind of one of the nicest aspects of the theory. And that's what allows us to also have a nice, robust argument supporting the experiment that I was talking about, because it's rooted into this more general framework. And the more general framework is basically based on the mathematics of set theory and these constraints on transformations that are possible or impossible. And these statements can be made without using the full apparatus of quantum theory equations. And that's why I thought that this was a very nice angle on entanglement and other phenomena, because basically you emancipate the description of these phenomena from quantum theory's formalism itself. So in that sense, it gives us a deeper operational understanding of what these things are.
Okay. Let me follow up on that. You introduced a new principle, which you call the interoperability principle. Is it a new principle? Is it an addition? Is it something that you propose to test? Is it a replacement for some other principle? What is this interoperability principle, and how does it relate to and or extend normal textbook quantum theory? And does the experiment have anything to do with testing for this interoperability principle?
Yeah, so that's one of the pillars of this constructive theory of information, which is precisely this framework where you can talk about both quantum information and classical information in this more general domain, where you don't have to commit to the formalism of either of them. And the principle itself is basically expressing an informal property of systems that can contain information. So what we know of, for example, 2 bits. If you have a system that you can use as a bit, like a switch, and then you have another system that's also a physical embodiment of a bit, which could be a flag with colors, for instance. Even though they're different systems, the idea is that you can always put them together into a composite system and treat the composite system as a system that can contain information itself. And the dimensionality is usually additive. So in a sense, you have 2 bits worth of information when you address the 2 systems jointly. Now, this may seem obvious in the case of the systems I mentioned, and maybe even in the case of quantum systems, like if you have a photon with polarization being the degree of freedom that you're using for binary encoding, and then you have another electron with a spin, you put them together in a quantum computer and you're hoping to be able to translate the information in one of the 2 qubits to the other. But if you think about it at the level of what this requires in terms of interactions, it's a very non-trivial requirement, because it basically requires that information is copyable from one side to the other of this, and vice versa, of this bipartite system. So whenever you have information-bearing systems that can contain information, you put them together, you always expect the full composite system to be addressable as an information medium itself. That's what the principle requires of theories that are physically viable. And it's a strong axiom. It's a bit like the axiom of locality, or the principle of locality. And this, together with the principle of locality, is what we are using to prove this result at the foundation of the experiment. So if the experiment were to be producing a negative result, so if you were not to see entanglement, it could be that one of these principles that we were using to predict the effect and to make the statement that anything that can entangle 2 systems must be quantum, it could be that some of these principles are wrong. So we are indirectly testing these principles, and particularly this information theory principle that you mentioned, the interoperability principle.
Okay, so that leads nicely into the next question. We're getting closer to the end of the list here, just about 4 more questions for me. Can you describe or discuss the relationship of constructor theory to information theory, classical and quantum versions, and to thermodynamics?
Yeah, so the short answer is that it's more general than these things. So it's supposed to provide like a further layer of explanation if you're thinking a deeper layer or whatever foundation for these theories. So classical information theory is, let's say, if you think of it as a physics-based theory, is implicitly assuming a discretized version of classical mechanics, of Newtonian mechanics, if you like, appropriately modified with locality and no signaling and so on. So it's basically classical physics with a discretized structure on top. And that essentially means that whatever variable you're using to describe a system, that has to be perfectly measurable together with all the others. That's what classical means. And this is never discussed explicitly in classical information theory. We only talk about communication channels, Shannon's capacity, results that already assume this physical basis to be there, this classical physics being the underlying support for all these theorems that are proven in the classical information theory. So that's more like a theory that doesn't care about physics. It's just deriving certain results about what happens if you're communicating or computing in the context where classical physics is true. And then quantum computing, as I said earlier, quantum information theory is assumes instead of classical physics, that quantum theory is the base. And then it explicitly uses quantum theory's equations, like Schrödinger equation, to compute results. And again, it's rooted into that. And so if you wanted to make it more general, you would have to change the rules again. So constructive theory provides a kind of framework where you can talk about both and more. So you have possibility of talking about phenomena like channel capacity, copying, information processing, and then quantum phenomena like entanglement, quantum superposition, quantum coherence. But in theories, they may not be quantum. They may not be classical either. They could be in between. And it could also be post-quantum theory. So ultimately, as a physicist, I'm interested in this theory that comes after quantum theory. And I'm hoping that these principles in constructive theory of information help us shape this new theory, right? So it's a bit like thermodynamics. It's like provides a sort of meta level that guides us to guess future theories of physics. And relation to thermodynamics is similar in a sense that thermodynamics is, well, similar, but not really. So the differences are in a different aspect of constructive theory. So thermodynamics is a theory that was initially formulated as a principle theory. So, there's the second law of thermodynamics, conservation of energy. All of these are like axioms in a sense, and they were assumed, and then people derived certain bounds on efficiency for heat engines, etc. But they have always been formulated at the macroscopic level, so they are scale dependent, right? And then we had Boltzmann and all the statistical mechanics studies that allowed us to connect these macroscopic descriptions with the microscopic dynamics that we know about microscopic particles that compose large systems. However, constructive theory principles are scale independent, and there are some versions of the principles of thermodynamics within constructive theory which they're not dependent on scale. So they are true not just in the thermodynamic limit or at the macroscopic scale, but they're also true of engines that use very few particles, not just in the thermodynamic limit. And so again, this provides a nice generalization of the principles of thermodynamics in the sense that they become emancipated from the issues of scale. And so that's the relation to thermodynamics.
Okay. So you say this would open a first experimental window on the future fundamental laws of physics. What is the window that you're trying to open? And what, if you open it, you're either going to see something or you're going to not see something. What question is going to be answered when you open the window and look through it? How and in what way might this reveal new physics or not? Like, there's a chance you open the window. I want to understand what happens when you open this window. What are the different things you might expect to see, and what is the new physics, if any, that might or might not be revealed?
So the first thing to say is that the window is much more openable than in other cases. So the big deal is that, unfortunately, in physics, despite the fact that it looks like we are producing lots of papers and lots of new things, actually at the fundamental level, we've been quite stuck with, just these two theories. It's been a century now, and we know they clash. There are some theoretical proposals to put them together, but they, have issues at the mathematical level. They're inconsistent, physically speaking. And the third issue is that they can't be tested easily. I mean, at least we thought so until this experiment was proposed. So this has been a huge stumbling block, because if you don't have experimental evidence that say that your theories are incorrect in their predictions, it's very hard. You can, but it's difficult to be guided into making guess for the future. And so the fact that this experiment allows us to even open some window is a really big deal, I think. And I think we should look for more of these experiments. I'm sure there are more.
Right. But you have a proposal for a low energy window, like we can do this. Okay.
Yes.
Now, let's say we do. What is the outcome? What are the, let's say,
okay, so
possible outcomes, and what are the ramifications for physics?
One outcome is that, as I said, you do see entanglement. That means that gravity, as described by relativity, is incorrect. So relativity has to be modified into a quantum theory. This would not automatically mean that current quantum gravity proposals are correct, because the experiment doesn't tell us which quantum gravity works. It just says that gravity has some quantum features. And so this would basically be a very strong motivation into looking for a viable, credible proposal for quantum gravity. And there are some that have been put forward, as I said, they're problematic at various levels. So this would be like this version of the window being opened would really motivate us into looking into providing a credible candidate. And this may mean also to modify some of the way we think about quantum field theory and use maybe different methods. I think we're not being creative enough in that direction. So I think this would provide really a strong push into finding a good candidate. That's one possibility. The other possibility is that, which is the one I'm not expecting, but if it were to happen and you do the experiment according to all the prescriptions, and then you don't see entanglement, that, assuming that you haven't neglected some extra, so there could be different scenarios. It could be that there is an extra noise source that you haven't taken into account at that scale. That could be an unknown field, because these are scales that haven't been probed before. So it could be that opens a window onto, yes, you would see entanglement, gravity is quantum, but it's blurred by this extra noise produced by an extra field, which we don't know about. That's one possibility. The other possibility is that quantum theory is wrong in some way. And that, again, would motivate us into finding variants of quantum theory that are viable. It's really difficult to come with a viable variant of quantum theory, because as soon as you try to vary Schrödinger's equation in some way, for example, nonlinear modifications, they clash with no signaling, for example. So you have lots of constraints that are very tight. And we haven't found yet a viable modification.
Okay,
so very excited.
We won't go down the whole road that collapse is certainly non-unitary. And I'm sure we could have a side discussion on that. Are we going to violate linearity, unitarity, these sorts of things? I understand what you're saying. That was a very clear answer. Thank you. Now I'm going to switch gears a little bit and come to the end. So is this a research program? Like, is there a whole team of people at different places looking into this? Are you a lone wolf, or are you part of a group that is collectively elaborating this?
So the Constructive theory broader program is a program of research, and I have some students collaborated that are working on this, and there are some other groups around the world that are doing various studies in different directions, not necessarily about the gravity experiment. The quantum gravity experiment specifically has hit some button that has ignited lots of fires around. So there are many experimental groups, many by the standards of these kind of foundational experiments, let's say 4 or 5, that are looking into realizing this experiment in different technologies. And I'm collaborating with a group in Turin and in Oxford also, where we are trying to actually build these interferometers. So there is a strong team that's trying to realize this interferometer with a nano-diamond. So that's a kind of trapped nano-diamonds in a lab. And so the race is on. I think people will realize this. Of course, it's a 5 to 10 year horizon. It's not something that you do in a year, let's say, because it requires a lot of fine-tuning. It requires also fundraising and so on. But I think it's a very exciting thing. And I'm hoping this also will inspire other experimental proposal of this type that explore similar effects. So yeah, that's the current state of affairs.
Okay, so you have several groups that are working on different experimental proposals, including a nano-diamond interferometer experiment. Is that what's next? Are there other things that are next? What's next in your research agenda?
So from the experimental point of view, I'm not an experimentalist, so I'm mostly, theoretician who is very optimistic, and then when talks to experimentalists, and then experimentalists sort of explain to me there are lots of various things that may go wrong along the way. But I think that's the kind of, that obviously requires a lot of work on even just the engineering side of things. So that work is being done in collaboration with me and Vlatko Vedral, who is just here in Oxford. And other groups, also theory groups around the world, are looking into this in parallel. So there's a bit of a competition going on there. But I'm not directly involved in the experiments, so I'm not doing the experiments myself. On the theory side, so my future works are on the theory side. And so there are like smaller increments and then the bigger vision. So the smaller increments are really just to think of interesting modifications of the experiment to make it simpler. So these can be always thought about. And I think I have lots of young collaborators who are working on these things with me and Vlatko. And that's very exciting. But then on the vision, from the kind of more visionary point of view, I really like this fact that constructive theory allows you to think of phenomena that are embodied in quantum systems without using quantum theory as the way to describe them. So I developed this terminology, the physics of hybrid quantum systems, to describe the systems where you have one side that is a true quantum system like a qubit, and then you've got another side that may deviate from quantum theory. Gravity is an example, but then you can think of a biomolecule that's mesoscopic and therefore could collapse away from quantum theory. And there are other examples as well. And I like to use constructive theory's principle to imagine experiments on these hybrid quantum systems. And I'm devising various experimental proposals to, for example, even relevant for quantum biology, not just for quantum gravity, where constructive theory's principles are like the things that are used in order to predict what can happen in these experiments. So that's a big sort of area of work. And ultimately, this goes under the label of witnessing quantum effects where you don't expect it. In macroscopic systems, some people even talk about these quantum effects in macroscopic biological organelles in various parts of someone's, even a human body and so on. I'm not particularly thinking of any of these things, but I think my schemes are very general and can be adapted to these things. And so that's a kind of very interesting direction for me. And the last one is the looking into the relativistic direction. So these principles are like quantum information theory. They don't take relativity into account because also this experiment is low energy. So you don't really need to think about relativity much in the sense of relativistic effects. But I would like to make these principles that we have in constructive theory relativistic compliant. So that's a big direction of understanding how relativity fits into this possible and impossible task type description of physics.
Thank you so much. Lydia, perhaps we should open it up to the general audience questions at this time.
I think that's a great idea. Does anyone in the audience have questions?
Yes, I left a question in the chat.
Oh, great.
So there's another question in there from somebody else.
Well, Eric, this is you, and you ask, can the experiment be done on a chip in a way that's similar to quantum optics experiments that are being done on a chip instead of on a lab scale optical bench or much less in space? Yeah, what's the scale of these experiments, and tell us more about this nano-diamond and, what's involved, whatever you want.
Yeah, so in principle, the answer is yes, in principle, in the sense that, as I said, the things that we are investigating are things that have been studied a bit more in detail, but doesn't mean that other platforms wouldn't work. And the scale is, the extent of the superposition is about a micron, and then the distance between the two interferometers is 100, 200 nanometers. So, sorry, microns. So I think the whole scale is that. And it can be placed into a trapping system in our own scheme. But it could be realized in a different geometry, which may not change the scale of the actual systems that much, but it may vary some of these parameters because you always have the mass and the distance between the two interferometers and the time for which you have to sustain the superposition, which is about a microsecond. And so all of these parameters are presumably similar across different implementations, but we don't have a study of that. So, it would be nice to have more groups who look into these things. So I would say that there is a lot of room for further studies, and I'm hoping more people think of different implementations so that one of them gets realized.
Okay, thank you.
Ben, how about you? You have a bunch of stuff in the chat.
Hi, folks. I'm Ben, and I came across this research and proposed experiment a while ago, and I just wondering what are the, because this is a space group and I'm a space fun myself, what are the implications of this proposed experiment in terms of potential technologies? Like, if we can witness a quantum effect mediated by gravity, like, and then that would mean that gravity is quantum, and that would mean that gravity is quantized. Like, would that mean that we can generate gravitrons in some way, or trap them and reuse them? Like, I was getting quite excited and hopeful about even the potential of anti-gravity and realize my sci-fi dreams.
Yeah, that's a really nice question. I think so. The more down to earth reply in terms of technology, I think, is just the fact that these things that we are developing would open the door to a much more sensitive type of sensor. So a gravimeter, which uses the sensitivity needed to test the entanglement in this platform, would be kind of really new tool on the metrology sensing type direction of research, of technological research. So that's the thing that's more within reach. But I think, as you said, what is interesting is that because this experiment would also open the door to new theoretical ways of thinking about gravity and quantum gravity, because it would motivate the search for the quantum theory of gravity, which we currently don't have. This will open the door to ways of incorporating gravity into our technologies, which we can't imagine at present. And I mean, anti-gravity is something that's, as you said, is like science fiction type thinking. But there are a host of other effects which we can't really imagine now, and they will be unlocked by the quantum theory of gravity. And so if the experiment tells us that gravity is quantum, and then we proceed on to finding a viable theory of gravity, we will also have better ways of testing it. And this will allow us to imagine these new effects. It's a bit like thinking of quantum light, right? When we quantize the electromagnetic field, then, down the line, many years after, you had something like a transistor, right? And then, all of the thing that the flurry of discoveries that came out of that. Of course, thinking of a photon and what it means, the fact that there is a photon, connecting it with various other phenomena, that kind, I think, is difficult to imagine. But this is something that was discovered along the way. And then lasers, and then various other technological developments that were created. So likewise, the quantum theory of gravity would unlock these things. Similar things, things that we can't imagine at present. So I think it's extremely important to look into it, because I think we're running out of fuel. If you think that all the medical discoveries, for example, diagnostic machines that we're using now for medicine are based on quantum effects, and all the technology that we are using now in classical computers are based on quantum, on the fact that the electrons behave in a certain way, and that ultimately we're using quantum theory to describe them. The structure of matter, all of these things actually gave us the discoveries that happened 100 years ago are now fueling the technological progress we've had so far. But at some point, we'll run out of steam. So we need another push for some of these fundamental discoveries in physics to go forward. And this is one way of unlocking this potential, which is why I'm so excited about it. Thanks. Yeah, thanks for the question.
Sweet. I think we have another question from Keith.
Yeah, I wrote it in the chat as well, but I can say it out loud. And it's a particular interest of mine if there's been any work in the constructed theory of knowledge, any progress on that front, or are you mostly focused on the gravity these days?
Thanks for the question. I think I've had mostly my recent work has been focused on these more physics-related applications. Although I should say that's maybe a bad way of saying it, because what I really liked about constructive theory and the way to think about knowledge in this framework is that it allows us to think of knowledge as a physical system, or as a physical property of physical systems. And so despite I haven't worked on it directly, but I think I have a lot of hope and expectations for this concept to be used largely in tying the physics of the mind to physics, because currently we don't really have a good physical theory of how the mind works. There is, of course, lots of progress in neurosciences and understanding at the higher level, but I would say it's mostly descriptive and a bit like in some aspects of biological functioning of the brain are clarified, but it's difficult to link this description with how thinking works. And how thinking works is a question for physics because it's a bit like asking how does a computer work, and that's also a question for physics. That's how quantum computers were discovered, right? Too. So in that sense, I don't have any particular progress to report other than my work in the constructive theory of life, right? That's a relatively old work. But I think the tools in there and the tools of constructive theory more generally are really important in this area. So I'm hoping there'll be more progress at some point in this direction. Thanks.
Okay, Lydia, should we close?
Yeah, speak now or forever hold your peace.
Thanks a lot for this interview. This was far better than any talk I could have constructed. So really, thanks for it. It was fun. Yeah, I enjoyed it too.
It was fun too.